That chapter 24. This is number 24 from chapter 4. And these are sex-linked problems for the most part. They probably all are, I would imagine. And so it's just a matter of thinking about, so Drosophila, yellow, that's not going to work. So we have yellow is X-linked. So these chromosomes just happen to be yellow. Doesn't have to mean that they're any more yellow than anything else. Meaning that just because it's not yellow because the gene's yellow. So that's yellow. And that's gray. And gray is wild type. So then a homozygous gray female. It really helps to just write down your symbols. And you say homozygous gray, well, we know homozygous means two of the same thing. And gray, that's the symbol for gray, is crossed to a yellow male. What do we get? We can get X plus from here. And that can go with an X with a little y. We can get this X plus. And this y. Well, we don't have to write them all down. So we can get an X plus and we can get an X with a little y. We're going to get X plus with a y. That's all we can get. And this is a wild type female. And this is a wild type male. So that's what we get in the F1. So what did we get? We had a heterozygous female in the F1. And we had a wild type male. And now what do we get? Now we can get the X plus from here. And that can go with the X plus from here. That would be a wild type female. We can get this X plus. I want to keep my males and females together with this Y. So that should be a big Y like this. Now we can get this X, a little Y on it, with that X with a plus on it. Or we can get this X with a little Y on it and a Y. This is a gray female. This is a gray female. This is a gray male. And this is a yellow male. We're calling these wild type, so gray is the same as wild type. So we can say we have 1/2 wild type female, 1/4 wild type male, and 1/4 yellow male. And so that's characteristic of sex linkage. If you do the cross in this particular way, it shows up at the F2. Remember, this is the F2. And so we have a difference between males and females. Our females are all one type, but our males are 50-50 gray and yellow. So because we see a difference between those two, that means it's sex-linked, because the difference is due to a difference in sex. All right, so now this is looking at a different type of cross. Now we have a yellow female. So a yellow. So we have a yellow female. So it's a female. So it has 2 X chromosomes. They don't tell us it's homozygous, but we know it's homozygous because we know that yellow is recessive. Cross to a gray male. Doesn't tell us whether he's homozygous or heterozygous because he can only be one thing. And remember that males aren't homozygous or heterozygous. So homozygous means you have 2 of the same thing. Heterozygous means you have 2 different alleles. Hemizygous means you only have one allele. So hemi means half, so you only have half the number of alleles that are possible. Because there's no allele here at all, because that's the Y chromosome. I should make this more of a big Y to distinguish it from this little Y over here. Now, if you get this case, so now we have a yellow female and a wild-type male. If we have an X-linked recessive trait, that means always all of the males are going to show the trait. Because if we have an X with this little Y, we have to get that from mom, and then we have to get this Y from dad, and so all males, so all sons, are mutant. And in this case, that's yellow. And the females will get one of these X's and we'll get that X, and they'll be heterozygous, and so they'll be wild type. So then we got to cross these guys together, which means we have to remember what they are. I think I can. All right, so we could cheat a little bit. We know we had a yellow female crossed to a wild type male. Not really cheating, we're just restating the problem. And so we've got our females were heterozygous. If I can remember to do it, I try to keep the females on the left and the males on the right, but there's no real rule for that. And our males were all yellow. So that was the F1 from the first cross. And now we can get this X, and we can get that with this. We can get, well, let's keep our females together. I like to do it that way. So we can get this X with that one. And then we can get either this X or this X. And if we get those, we can get a Y. You could certainly do a Punnett square if you wanted to. I just like to do it that way. So yellow female, wild type female, yellow male, wild type male. Or we could say they're half yellow and half gray, or wild type. And there's no difference in the sex. So it's not that the males and females aren't different here. The males and females were different here. So this was the original cross that gave us this. And the males and females were different. We had wild type females, mutant males in the F1. So because we had a difference in the F1, that tells us that it's sex-linked. And then this just happens to be what you get when you cross it. So another key, so sort of a key, what we actually did right there was we did a reciprocal cross. So we took a yellow female in one cross, actually this was the second cross, crossed to a wild type male, so that was one cross. And we took a wild type female and a yellow male, and that was a different cross. These are reciprocal because we're using the mutant is male in this case and female in that case, so they're different. And so then we get different results. In the F1, we get yellow males and wild type females. Here in the F1, we get all wild type. So even if we don't go further, by doing the reciprocal cross and seeing that we get a different result, that means, here we'll change colors just to be crazy, that means they're sex-linked. Because we have a difference in sex in the when we do the reciprocal cross. So that's it. So then we can go on to C for this problem, if I can find it. So there's C. So now we have a yellow female. Yeah, we'll stick with red for a while. So yellow female, crossed with a gray male. F1 males, F1 females, sorry, so we got F1 females. They have to all be this. So we don't have to worry about anything else. We know we get that chromosome and that chromosome, F1 female, are back crossed with gray males. So that means they're crossed back to a parent, in this case, the gray male. And what do we get? We're going to put this over there so we can, so we can get this X. If we get that X, we can get this X. We can get this X. And this X. We can get this other X, the first one, and a Y. We can get this X and a Y. There's various ways to do it. I mean, you can take this X and put it with that, and then take this X and put it with that. However you want to do it, you can do a Punnett square. Punnett squares for one gene aren't too bad because they don't take too long. So this is a wild type, female. Wild type, female, yellow, male, yellow, male. So it's pretty similar to the other cross. So it was basically the equivalent. Well, it just is what it is. Now D for this cross, I might not have even put D in here. D was a little bit complicated, so we're not going to worry about it. It was asking if you took a bunch of different F2s and let them mate together, what kinds of things would you get in the F3? Yeah, it's fine, but it's not really worth doing at this point. So that's question 24, and it's your sort of standard sex-linked cross. Okay, so this is a different type of problem. It takes a slightly different type of reasoning. We're still using the same principles in that we're talking about sex-linked genes, but rather than just sort of giving you everything up front and saying what it would happen if we crossed these things, it gives you some information and then asks you to fill in some of the genotypes. So we know that miniature wings is recessive, because we know that because it has X and a little m, and it also says it's recessive, X-linked recessive allele, to wild type, or long, which is X plus. Give the genotypes of the parents in the following crosses. So here we get the parents, and then we see what the offspring are, and we can look at the offspring and then infer back to what the parents are. And so here's a male parent that's long. The male, we always know what the male is because the male has to have an X and it only has one X. If it's long, we know that it has that allele and we know he has a Y. The female parent's long, so we know that she has an X. Well, I put long, but so we'll put a plus. And we know she has another X, but we don't know what's here yet. And so, really, whenever you're doing this sort of thing, if any miniatures come out of here, you know that there has to be a miniature allele somewhere. So because we see some miniatures coming out, then that miniature allele has to come from here, because it's the only spot we have. So if she was homozygous for this plus allele, then we'd only get long coming out here. And then once we put in these alleles, we can check to see if it makes sense. We could get X plus, that's the long female. We could get X plus XM, that's a long female. We can get this X plus from here, and a Y, that's a long male. We can get this XM from here, and a Y, that's a miniature male. So that's the basic logic behind it. Here we have a miniature male. So we know what his genotype is. And we have a long female. And we know she has an X, but we don't know what's up here yet. Everything that's coming out of here is long. If she had a little miniature allele here, then you could get miniature females and miniature males, but you don't. You don't get anything. You get all long. So she is has to be homozygous. The other thing that is useful to think about here is, if we had only looked at 2 flies, we wouldn't really know. It's possible that if we did 2 flies that they would both be long. But when you look at this many, that's a decent amount of offspring, and that helps to give you confidence in your conclusion. So again, the males are always on the left here. So we've got XM, Y, we always know what the male is. We've got the female, is that. We don't know what this is, but if it was plus, we'd get all long here. We just saw that in the previous one, so that has to be little m. And then we can get, because we had a little m here, we can get XM, X plus, so we can get wild type females, we can get XM, XM, we can get miniature females, we can get this X plus and a Y, so we can get long males, we get this X and a Y, so we can get miniature. So we can get all the different combinations. Here we have a male, X plus Y, a female, we already know her genotype, so that's all we need to know. Because miniature is recessive, we know if we have a female who has miniature wings, then she has to be homozygous recessive. And then this is one of those crosses where you have a female who's mutant and a male that's wild type. And over here, I don't even remember over here which one were male and female, but these must be the males. Because the males are all going to get this X and this Y, and so they'll be all miniature. And the females will get XM from here, either this one or this one, and then they have to get the X plus. So they'll all be long. So with these things, it's a good idea just to be systematic and to go in what you know and then fill in the rest. So here we have a male is long, female is long, all we get is long, so she's probably homozygous. Simple enough. This gives us an example of a human sex-linked cross. And so these we start to think about pedigrees. You don't have to do pedigrees, but I like to do it that way. And so, actually we don't even have to. So red-green color blindness is an X-linked recessive trait in humans. So color blindness, we get a little c, that equals colorblind. And we can say X plus equals normal vision. Polydactyly, just give him a little polydac. Extra fingers and toes is an autosomal dominant trait. So we'll say big P is polydactyly, little p is normal. And then we have Martha. So we might need a little more room here. So Martha has normal. All right, so Martha, let's just do regular things. So Martha has normal fingers and toes. Fingers and toes. And so if she had a big P, she would be polydactyly and have extra fingers and toes. So we know she has 2 little p's because she has normal fingers and toes. She has normal color vision. All right, so we know she has at least 1 X plus, but we don't know what she has here yet. We're still trying to figure that out. Her mother is normal in all respects. So her mother also has a big plus, but she could be a carrier for that. And we know she has 2 little p's. Her father is colorblind and polydactyly, so he got the bad draw, I suppose. I don't know, maybe it's good to be polydactyly. So that means you had to get this X from Dad, so that means we know she's a carrier for that. His mother has normal vision and normal fingers and toes. Oh, so wait, where's Bill? Bill's in here somewhere. Oh, that was Bill. No, her father, yeah, her father was colorblind and polydactylous. Bill is also colorblind and polydactylous. So Bill is colorblind and polydactylous. His mother had normal color vision and normal fingers and toes. And so what that tells us, so she had normal color vision, she was a carrier, and she had normal fingers and toes, so she had two little P's. So that's just telling us that he got a little P here. And for all that, if Bill and Martha marry, so this is Martha, this is Bill, what types and proportions of children can they produce? So the point of this problem is to show you that you can analyze genes separately, and you can just figure out what's going on with the X-linked genes, figure out what's going on with the polydactyly gene, and then just combine your information. So let's just double check and make sure we're good here. So Martha, normal fingers and toes, good. Normal color vision, she's got a big plus. Her mother is normal in all respects, but her father is colorblind. She had to get one of the X's from her father, so she had to get that little C. Her father was also polydactylous, so that's over here, but she's normal, so she must have got the little P from him. Bill is colorblind and polydactylous, so he has to have the little C, and even if they didn't tell us about his mom over here, we probably could have guessed that he was heterozygous. Make this obviously bigger, because usually if it's a dominant trait, it's very unlikely to be homozygous for it. It's not impossible, but it's unlikely. So if we look at the X chromosomes, what can we get? We can get X plus from here and XC from here. We can get X plus and Y. We can get this X with a C on it and X with a little C on it. We can get that X with a C on it and a Y. So we can get normal female, colorblind female, I think that was a plus, normal male, colorblind male. So essentially we have 1/2 colorblind, 1/2 normal. All right, everybody that? I think I've got it right. And over here, this is sort of like a test cross. We've got we can get one, this is just an autosomal trait. So we can get, from here we can get either a big P or a little p. So that's why it's hard to use P's sometimes, that's a big P. And then we have to get a little p from here. So that's like a test cross. So what can we get? We can, if we multiply these together, we're going to get 1/4 are colorblind and polydactylous. 1/4 are colorblind and normal. 1/4 are normal and polydactylous, and 1/4 are normal and normal. So we'll just say normal. Now we'll put it both ways. And the way we do that is we just take this 1/2 colorblind, so that's a probability that you get colorblind, and 1/2 probability that you get polydactylous, multiply those together, and that gives you this. So I think that's basically it. And the point is, again, multiplying probabilities. You can have all kinds of crazy stuff going on with each individual gene, but if you just analyze each gene independently, figure out the probability for that gene independently, and then figure out the probability for the other gene independently, and then multiply those probabilities together, you get this. That, of course, depends on independent assortment, but independent assortment means that genes are on different chromosomes, and we know that these genes are on different chromosomes because this one's X-linked, and this one's autosomal. And autosomal, that means it's on the X chromosome. Autosomal means it's on something else. And so if it's on something else, it's not on the X. They're on different chromosomes. So we get independent assortment. We'll see later that if you have two genes on the X, you don't get independent assortment, and those genes are linked. So this is another one, similar idea. You'll almost be guaranteed to get one like this on the exam. This is just looking at two genes. One of them is X-linked and one of them is not, autosomal. So you have to. So a lot of times students will come up to me and say, "Oh, what does autosomal mean?" But you need to know what autosomal means. So that's one of those terms you need to know. So miniature wings and Drosophilas due to X-linked recessive, and sepia is autosomal recessive. Sounds good enough. So we have a female fly that has miniature wings. And she has sepia eyes. Well, that's easy enough. If she has sepia eyes, because sepia is recessive, she has to be homozygous. A male has normal wings. And is homozygous for red eyes, so that was big S, big S. Cross those guys and get an F1. The F1 are all females going to look like this, so they're all going to have normal eyes, and they're all going to be heterozygous. And the males are all going to be miniature wings, and they'll also be heterozygous for sepia. So what do we get out of that? So now we just have to figure out the result of this cross. We'll do it in red. We'll make our results in red. So let's just do the X-linked genes over here. XM, XM. That's a miniature female. X plus XM. That's a wild type female. XMY. X plus Y. Again, so what I do is I take this one and I combine it with this X. Then I take this one and combine it with this X. I do that just to keep my females in one spot. You don't have to do it that way. And then I take this X, combine it with this Y, and this X and combine it with this Y. Then we got our males down here. So we got female, male, miniature, wild type, miniature, wild type. But there's no difference in sex here, so we can just say 1/2 miniature, 1/2 wild type. Alright, let's go nuts and do another color so that we can keep our genes separate. So now, sepia. That's a monohybrid cross. We know what that gives us immediately. We don't have to think about it. So then we can get miniature and wild type for wings. We can get miniature and sepia. We can get wild type wings and wild type eyes. We get wild type wings and sepia eyes. So this is just a shorthand. If you don't like that, throw in a WT. But just sort of get tired of writing down all this stuff. So how many are miniature and wild type? meaning big S. Well, 1/2 or miniature times 3/4 is 3/8. Miniature and sepia is 1/8. Wild type and normal is 3/8. And wild type and sepia is 1/8. That's sort of how that goes. Notice that if you have, if we ignore the wing here and we just look at wild type and sepia, we get 3:1. Wild type and sepia, we get 3:1. Miniature and wild type, half, 4/8 are miniature, and 4/8 are wild type. So that's half and half. So that just means that these ratios are still present over here if we just look at each trait independently. But then when we combine them, we get these other numbers. And so that's our answer. The same genes, we're doing the cross a slightly different way. And we know that if we have X-linked genes, that it matters how we do the cross. It matters what kind of male we use and what kind of female we use. For the sepia, it doesn't matter because that's autosomal, so it doesn't matter. So female fly, homozygous for normal wings. Because we're starting out green this time. She also has CPIs. Male that has miniature wings and is homozygous for red eyes. Sorry. That would be two. So if you ever try to do a cross and you put two females and no males in there, you're not going to get any babies. Alright, I'm going to zone it out here. So, what do we got here? So he's got, and he's homozygous for red eyes. Alright, big. Alright, so we already know, so the F1, X plus X, M, this and this, X plus Y, this and this, across those two. So we already know 3/4 to 1/4, because that's a monohybrid cross. Monohybrid crosses always give you the same thing. But what's going on with the X chromosome? Let's do that one in red. X plus, get a normal winged female. XM, X plus, we get a normal winged male. Normal winged female. We get X plus Y and XMY. So overall, we get 1/2. This should look familiar. Wild type female, 1/4 wild type male, and 1/4 miniature male. So because we get a difference here in the phenotype of males and females, that means it's sex-linked. We already knew that, but that's consistent with it being sex-linked. But it also means we have to keep track of which ones are males and females. So then to figure all these things out, we just multiply all these guys together. Multiply that by that, that by that, that by that, that by that. So let's do that. Give ourselves a little bit of room. And we have 1/2 times 3/4 is 3/8. Let's do a different color. So we're going to have this 1/2 times 3/4 is 3/8. That's wild type for wings and wild type for eyes, and it's a female. Because there's a difference between males and females. We'll get 1/8 wild type sepia female. So that's 1/2 times 1/4 wild type sepia female. 1/4 times 3/4 is 3/16 wild type eyes, or wings, wild type eyes, wild type wings and eyes, and it's a male. 1/4 times 1/4 is 1/16. So now we've got wild type and sepia, and it's a male. We'll have to go over here for the other ones. So now we're going to multiply these by those two things. We get 3/16 miniature wild type male, and this one times this one, 1/16 miniature sepia male. So this is our answer. Now hopefully when you guys do this as a test, it'll be a little neater than this. It's a little bit hard to fit all this in with this pen. That's our ratio. And we just multiply them all together. And now you'll notice, if we can see what all these things are, you have for wild type and sepia, just for the eye color, we've got 3:1 wild type to sepia, 3:1 wild type to sepia. Over here, 3:1 wild type to sepia. So the 3:1 wild type to sepia always stays the same, and it doesn't matter about sex. But with the miniature wings, we've got all of our females should be, so these are all our females. And so 4/8 of our females are wild type. And then our males, we have 3/16 and 1/16 that are wild type, 3/16 and 1/16 that are miniature. So half of our flies are wild type females, 4/16 of our flies are wild type males, and 4/16 of our flies are miniature males. If we just look at each gene by itself, that's the same thing we got over here. So again, the individual ratios are still present in the overall data, the overall results. It's just when we combine them together, we have to keep track of the different combinations of phenotypes. That's because of independent assortment. All right, this one's kind of fun. So Joe is colorblind, and we have to think ahead a little bit and put him down here. He's colorblind, and we're just talking about one trait. His mother and father have normal vision. I'm not sure why I put him that far over there, but that's his mother and father. All Joe, his mother and father, his mother's father or maternal grandfather is colorblind. Put my grandma over here. Well, I guess put grandma over here. All Joe's other grandparents have normal color vision. So his dad's mom and his dad's dad have normal color vision. Joe has 3 sisters. Patty, Betsy, and Laura, all with normal color vision. Joe's oldest sister, Patty, is married to a man. Now, I don't care if she's oldest. I think that you do put these in order in terms of age, but we're going to put it over here so that we can fit it in. He's got normal color vision. They have 2 children. 9-year-old colorblind boy, and I think you would actually put the older one here, and a 4-year-old girl with normal vision. So he's colorblind. So there's the pedigree. Now, this is going to turn out to be X-linked, and you can tell because, well, we know that colorblindness is X-linked. There could be other kinds of colorblindness that aren't X-linked. But here it's affected, doesn't show up in this generation, shows up again in this generation, and then shows up again down here. Let's see. Okay, so that's fine. So what is the most likely mode of inheritance? We're going to go with X-linked recessive because it's only showing up in boys. And it's most likely. You know, the thing with pedigrees is we can't know for sure. You can't do controlled crosses to test out your hypotheses and that sort of thing. We can double check and make sure we did our pedigree right. So Joe's colorblind. Mother and father over here are normal. His mother's father is colorblind. All his other grandparents have normal vision, so this grandma, this grandpa are all normal. 3 sisters, Patty, Betsy, Laura, all with normal vision. Normal, normal, normal. Oldest sister, Patty, so this is Patty. She's married to a man with normal color vision. But they have 2 kids. All right. And one has color blindness, and it's a boy. All right. So we'll go with X-linked recessive. Now we know it's recessive. Anytime you have 2 unaffected individuals that give you an affected offspring, so these 2 are unaffected, this is affected, then it has to be recessive. Because it was dominant, then this individual would have to get the dominant allele from one of its parents. And if one of its parents had a dominant allele, then they would have to exhibit the trait, because that's what we mean by dominant. So if Joe marries a woman who has no family history of color blindness, what is the probability that their first child will be colorblind boy? Marries a woman who's normal. So Joe, this is Joe, he's going to marry a woman who's normal. So, and the question was, what's the probability of a colorblind boy? And so, part of this is just a symbol. You can write that any way you want. But that's just, I just wrote that so I'd remember it. So we have a 1/2 probability of getting a boy. And we want to know what's the probability of getting a colorblind boy. So we want to know the odds of getting colorblind. Well, he is so Joe's colorblind. She has no history of it. And so we assume that she is not colorblind and doesn't carry a colorblind allele. If there's no history of it in her family, we're talking about the most likely situation. So all these boys are going to have an X plus and a Y. So the probability of getting a colorblind boy is 0. But if he has a daughter, he could give her his colorblind X, and then when she had kids, some of her boys could be colorblind. And is there another one? So if Joe marries a woman who's a carrier of a colorblind allele, so now we're going to do carrier. So we know she's a carrier. That's a symbol for carrier. We know she's this. And Joe we know is this. And now the question is, what's the probability of getting a colorblind boy, their first child? Well, we know there's 1/2 probability of getting a boy. And what's the probability of getting a colorblind? Well, we have a 1/2 chance of getting the colorblind chromosome or the colorblind allele, and a 1/2 chance of getting the wild type. So the chance of getting a boy is 1/2. Probability of colorblind is 1/2. So 1/4 colorblind boy. So that's it for the set of problems for Chapter 4. There are more problems. We'll look those up. I just wanted to do some representative ones, and not necessarily all of them. And the problems you would get would look similar to this. But there's usually something in there that makes you think a little bit. But by the time we get to the exam, there's going to be a lot of different things to look for. And so if we could just do these basic things,